In linear algebra, vectors are fundamental objects that represent quantities with both direction and magnitude. Vectors can exist in any number of dimensions, but we commonly work with 2D and 3D vectors for visualization. In Python, we can use the NumPy library to create and manipulate vectors. The code provided uses the NumPy library to create two NumPy arrays, which represent 2D and 3D vectors. The first vector, vector 2D, has two elements, indicating it is a vector in two-dimensional space, while vector 3D has three elements, placing it in three-dimensional space. We then print each vector to visualize their components. Vector arithmetic. Vector arithmetic involves operations such as addition, subtraction, and scalar multiplication. Vectors are often represented as ordered lists of numbers called components, and these operations are performed component-wise. In this example, we will perform some basic vector arithmetic operations using Python. In the provided code snippet, two vectors v1 and v2 are defined using NumPy arrays. Vector addition is carried out by simply using the plus operator, resulting in adding corresponding components of v1 and v2. Vector subtraction is done using the mass operator, subtracting v2 from v1 component-wise. Scalar multiplication is also demonstrated, multiplying each component of v1 by the scalar value 5. The operations are vectorized, meaning they are automatically applied to each element of the vectors, thanks to NumPy library capabilities. Dot product and cross product. The dot product, also known as the scalar product, is an algebraic operation that takes two equal-length sequences of numbers, usually coordinate vectors, and returns a single number. This operation combines two vectors to form a scalar and is useful in finding the angle between the two vectors in n-dimensional space. This code snippet demonstrates how to calculate the dot product of two vectors using NumPy, a powerful library for numerical computing in Python. Two vectors, vector A and vector B, are defined as NumPy arrays. The np.dot function is then used to compute their dot product, which in this case would return a single scalar value representing the dot product of the input vectors. Complex numbers. Complex numbers are numbers that can be expressed in the form a plus bi, where a and b are real numbers, and I is the imaginary unit with the property I = -1. Complex numbers are fundamental in various fields including engineering and physics. Python has built-in support for complex numbers, which can be useful to simulate operations involving them. The code defines two complex numbers z and w. The z is defined using the complex function with real part 3 and imaginary part 4, while w is written directly with real part 2 and imaginary part 5 using the j notation. It then prints both numbers and performs addition and multiplication between them. The output showcases how we can handle complex numbers seamlessly in Python. Systems of linear equations. A system of linear equations consists of two or more linear equations with the same set of variables. The goal is typically to find the values of these variables that satisfy all equations simultaneously. The provided Python code uses the solve function from the scipy.linealg module to find a solution to a system of linear equations. A represents the coefficient matrix, and B is the constant vector. The function solve linear equations takes these as input and returns the solution vector x, which contains the values of the variables that satisfy the equation ax = b. If the system is consistent and has a unique solution, x will represent this solution. Gaussian elimination. Gaussian elimination is a systematic method for solving systems of linear equations. It involves using row operations to transform a matrix into row echelon form. From there, the solutions to the system can often be found by back substitution. The main row operations are 1. Swapping two rows, 2. Multiplying a row by a non-zero scalar, and 3. Adding a multiple of one row to another row. The code represents a Python implementation of Gaussian elimination. We define a matrix A and a vector B, which constitute the augmented matrix of a linear system. The goal is to transform A into its row echelon form and B accordingly, so that the system becomes easier to solve. The nested for loops apply the row operations to A and B. Originally, the diagonal elements are set to 1 by dividing the entire row by the diagonal element itself, and subsequent rows are modified to ensure that elements below the pivot diagonal element become 0 gradually building the row echelon form. This step is known as forward elimination. The print statements at the end show the result after the elimination process. Definition of a matrix. A matrix is a rectangular array of numbers, symbols, or expressions arranged in rows and columns. The individual items in a matrix are called elements or entries. Matrices are usually denoted by capital letters, and their dimensions are given by the number of rows and columns they contain. In this code, we're using the NumPy library in Python to define a matrix. The matrix A is created using np.array, with two lists corresponding to the two rows of the matrix. Each list contains 3 elements representing the columns, thus creating a 2x3 matrix. Being a 2x3 matrix means it has 2 rows and 3 columns. The print statements are used to display the matrix. Matrix addition and scalar multiplication. Matrix addition is performed by adding corresponding elements of 2 matrices of the same dimensions. Scalar multiplication involves multiplying every element of a matrix by a scalar, a single number. In the code, 2 2x2 matrices A and B are defined using NumPy arrays, which are then added to form matrix C, representing matrix addition. The scalar alpha is defined, and scalar multiplication is performed on matrix A to obtain matrix D. NumPy overloads the plus and star operators to perform matrix addition and scalar multiplication respectively when used with arrays. Matrix multiplication. Matrix multiplication is an operation that takes a pair of matrices and returns another matrix. The element at each position in the resulting matrix is computed by taking the dot product of the corresponding row from the first matrix with the corresponding column from the second matrix. For matrix multiplication to be defined, the number of columns in the first matrix must be equal to the number of rows in the second matrix. In the provided code, we're using NumPy, a popular Python library for scientific computing that provides an array object and a collection of routines for fast operations on arrays. The np.array function is used to create 2 2x2 matrices, A and B. The np.dot function is called to perform matrix multiplication between A and B. The result is an instance of NumPy array C that holds the product of matrices A and B. Remember, matrix multiplication is not element-wise. It involves a dot product of rows from the first matrix with columns of the second one. Transposition of matrices. The transposition of a matrix is an operation that flips a matrix over its diagonal, exchanging the row and column indices of each element. The transpose of a matrix A is often denoted by AAT. In the transposed matrix, the element at the position ij in the original matrix will be at position ji in the transpose. The provided code defines a function transpose that takes a matrix as input and returns its transpose. It then transposes a 3x2 example matrix, matrix A. First, it determines the size of the matrix, then uses list comprehension to swap the rows and columns, creating a new 2x3 transposed matrix, matrix or A transpose. The print statement outputs the transposed matrix. The identity matrix. The identity matrix, often denoted by I, plays a crucial role in matrix operations, particularly in the context of matrix multiplication. It is a square matrix with ones on the diagonal and zeros elsewhere. Multiplying any matrix by the identity matrix of compatible size leaves the original matrix unchanged, analogous to the way multiplying a num by 1 leaves it unchanged. The identity matrix serves as the multiplicative identity element in the matrix world. The code snippet creates a 3x3 identity matrix using the NumPy library in Python, which provides the I function for this purpose. I stands for I, the commonly used symbol for the identity matrix. The function np.r3 generates an identity matrix of size 3x3. When printed, this matrix displays the characteristic format of the identity matrix, with ones on the main diagonal and zeros elsewhere. Inverse matrices. In linear algebra, an inverse matrix is a matrix that, when multiplied by the original matrix, yields the identity matrix. Not all matrices have an inverse. A matrix must be square, same number of rows and columns, and have a non-zero determinant to possibly have an inverse. The inverse of a matrix A is denoted as A mace. The provided Python code uses the NumPy library to calculate the inverse of a 2x2 matrix A. Firstly, we import NumPy and create a matrix A as a NumPy array. Then we use np.linealinv to compute the inverse of A and assign it to A in V. Lastly, we print A in V, which will display the inverse of the original matrix if it exists. If A did not have an inverse, i.e. it was singular or non-square, the code would raise an error. Determinants. The determinant is a scalar value that can be computed from the elements of a square matrix. It gives important information about the matrix, including whether the matrix is invertible and properties of linear transformations represented by the matrix. The provided code calculates the determinant of a 2x2 matrix using the NumPy library in Python. After importing NumPy, we define a 2x2 NumPy array to represent our matrix. We then call the np.lineal.det function, which computes the determinant of the given matrix. Finally, the determinant is printed out. The determinant of this particular matrix can also be calculated manually using the formula AD-BC, where A, B, C, and D are the elements of the matrix A, B, C, D. Matrix rank. The rank of a matrix is the dimension of the vector space generated or spanned by its columns. It gives us a measure of the number of linearly independent column vectors in the matrix, and it is equal to the number of non-zero rows in its row echelon form. Computing the rank of a matrix can be done using various methods, including Gaussian elimination, or using built-in functions in software like Python with NumPy. The code begins by importing the NumPy library, which contains functions used in scientific computing. A matrix is defined as a two-dimensional NumPy array. The np.linealg.matrixRank function is then used to compute the rank of the matrix, which is the number of linearly independent rows or columns. The rank is printed out to the console. In this example, even though there are 3 rows, the second row is a multiple of the first, so they are not independent. Hence, the rank will be less than 3. Subspaces. A subspace is a subset of a vector space that itself is a vector space under the same operations of vector addition and scalar multiplication. To check if a subset W of a vector space V is a subspace, it must satisfy 3 conditions. It must contain the 0 vector, be closed under vector addition, and be closed under scalar multiplication. The code defines a function isSubspace, which determines if a set of vectors represents a subspace. It converts the list of vector representations into a NumPy array, checks if the 0 vector is included, and verifies closure under addition and scalar multiplication. It does the latter by iterating over all pairs of vectors and checking if their sum and any scalar multiple are still within the set of vectors provided. If all conditions are met, it returns true, indicating the set is a subspace. Otherwise, it returns false. Span and linear independence. Span is the set of all possible linear combinations of a given set of vectors. If the span of a set of vectors is the entire vector space, then those vectors are said to span the vector space. The code defines 2 vectors v1 and v2 in a 3-dimensional space using NumPy arrays. It then computes a linear combination of these vectors by multiplying v1 by a scalar alpha and v2 by a scalar beta, and adding the results. The output is another vector in the same space, which is a point in the span of v1 and v2. Basis and dimension. In linear algebra, a basis of a vector space is a set of vectors that are linearly independent and span the space. The dimension of the vector space is the number of vectors in any basis for the space, indicating the minimum number of directions needed to span the entire space. The code snippet defines 3 vectors in SPROS 3, and it uses the SymPy library to check if they form a basis for SNUF3. The reduced row echelon form, RRF, is computed to determine if the vectors are linearly independent, a requirement for them to be a basis. If the number of pivot columns equals the number of vectors, they are linearly independent and form a basis. The pivots tuple indicates the positions of the pivot columns, which we use to extract the basis vectors. The dimension is the number of these pivot columns. In this case, the dimension of the space will be the same as the number of basis vectors, indicating the space is Guth-3'd. Column space and null space. The column space of a matrix A, denoted as col A or range A, is the set of all possible linear combinations of its column vectors. It represents all vectors that can be obtained by multiplying A with some vector x. The code calculates the dimension of the column space for matrix A. It uses NumPy to define the matrix and np.lineal.matrixRank to find the rank, which corresponds to the dimension of the column space. The print statement outputs the dimension. Row space. The row space of a matrix consists of all possible linear combinations of its row vectors. It's a fundamental concept in linear algebra and is crucial for understanding the solutions of linear systems. Here's how to compute the row space of a matrix in Python using NumPy. The code performs the following steps to compute the row space of a matrix A. 1. It imports the NumPy library, a powerful Python library for numerical computations. 2. It defines a sample matrix A. 3. It computes the QR decomposition of the transpose of A. The Q matrix of the QR decomposition reflects the orthogonal basis for the column space of AT, which corresponds to the row space of A4. It extracts those rows that correspond to the non-zero pivot elements upon transposing Q back. 5. It then creates a basis for the row space of A by filtering out the near-zero numerical noise using a threshold of 1e10 to determine non-zero elements. The Rank-Nullity Theorem. The Rank-Nullity Theorem is a fundamental principle in linear algebra that connects the dimensions of the 4 fundamental subspaces associated with a matrix. Specifically, it relates the rank of a matrix, which is the dimension of the column space or the row space, and the nullity of a matrix, which is the dimension of the null space, to the number of columns of the matrix. The theorem states that for a matrix A with n columns, rank A plus nullity A equals n. The provided code snippet first imports the null space function from the scipy.linealg library. Then, it defines a matrix A and calculates its rank using the np.linealg.matrixScoreRank function. Following that, it computes a basis for the null space of A using the null space function. The nullity is determined by the number of columns in the basis for the null space. Finally, it prints the rank and nullity of matrix A, which, according to the Rank-Nullity Theorem, should sum up to the number of columns of A. Definition and examples. In linear algebra, a linear transformation is a mapping between two vector spaces that preserves the operations of vector addition and scalar multiplication. A function t from vector space V to W is called a linear transformation if for any two vectors, x and y in V and any scalar A, the following properties hold. T of x plus y equals tx plus ty, and tax equals atx. This means that the image of a sum is the sum of images, and the image of a scalar multiple is a scalar multiple of the image. Kernel and range. In the context of linear algebra, a linear transformation is a function that maps vectors from one vector space to another, preserving the operations of vector addition and scalar multiplication. For a linear transformation T from a vector space U to a vector space V, the kernel, or null space, of T is the set of all vectors in U that are mapped to the zero vector in V. The range, or image, is the set of all vectors in V that can be obtained as TU, for some vector U in U. The presented code snippet uses Python with NumPy library to demonstrate how to calculate the kernel and range of a matrix representing a linear transformation. NumPy does not directly provide a function to calculate the kernel, null space, so usually additional libraries such as SciPy would be required to find the basis for the kernel. However, the matrix rank function is used to determine the rank of the matrix, which reflects the dimension of the range. Composition of linear transformations. In linear algebra, the composition of two linear transformations is a new linear transformation that is the result of one transformation followed by the other. If we have two transformations, T1, V in a W, and T2, Wx, their composition, T2 for a T1, is a transformation that maps a vector in V directly to x. In the code above, we have two linear transformation matrices A and B representing T1 and T2 respectively. The composition of these transformations is calculated as the matrix product C equals B to A using NumPy's dot function. The composed transformation is then applied to a vector V, resulting in a new vector that represents the transformation of V under both T1 and T2 sequentially. This process of matrix multiplication and vector transformation exemplifies the concept of composition of linear transformations in a concrete computational form. The matrix of a linear transformation. In linear algebra, any linear transformation from a finite-dimensional vector space to another can be represented by a matrix. To find the matrix of a linear transformation, you need a basis for both the domain, input space, and the codomain, output space. You then apply the transformation to each basis vector of the domain and express the result as a linear combination of the basis vectors of the codomain. The coefficients of these combinations form the columns of the matrix. Here's a simple example using Python with the NumPy library. The code defines a linear transformation that takes a two-dimensional vector and maps it to another two-dimensional vector using the function 2v1 plus 3o2 for the first component and to1 minus do2 for the second. This transformation is defined in the linear transformation function. The standard basis for R2 is used here, and the transformation is applied to each basis vector. The result is a list of vectors that have been transformed. These transformed vectors are then stacked column-wise to form the matrix of the linear transformation by using NumPy's column stack function. This matrix represents the given linear transformation with respect to the standard basis. Change of basis. In linear algebra, the change of basis is a process that converts vectors in one basis to another basis. This process is often used to simplify problems or to represent vectors and linear transformations in a more convenient form. A basis change is performed using a transformation matrix known as the change of basis matrix. In the code, we start by defining two bases, B and C, each comprised of two vectors b1, b2, and c1, c2 respectively. These vectors are arranged into matrices B and C by stacking them as columns. To find the change of basis matrix P that transforms coordinates from basis B to basis C, we first compute the inverse of matrix C, C in V, using NumPy's linear algebra inverse function. Then we multiply C in V by B to get the change of basis matrix P. When this matrix P is applied to a vector in basis B, it will transform it to the coordinates in basis C. Similarity transformations. Similarity transformations refer to a relation between square matrices. Two matrices A and B are similar if there is an invertible matrix P, such that A equals PBP nanosmall. This transformation is a change of basis in a vector space that preserves the structure of the matrix. This code snippet shows how to compute a similarity transformation in Python using NumPy. We define a matrix A that we want to transform and a matrix P, which is our basis transformation matrix. We use @ for matrix multiplication and np.lineal.inv to find the inverse of P. The result B is similar to A via the basis represented by P. Definition and properties. In linear algebra, an eigenvector of a square matrix A is a non-zero vector V that, when multiplied by A, results in a scaled version of V, where the scale factor is known as the eigenvalue lila, corresponding to that eigenvector. Formally, this relationship is written as AV equals LV. The definition is fundamental in understanding how eigenvectors and eigenvalues are reflective of the matrix's properties. They are particularly important in applications such as stability analysis, vibrations analysis, and in simplifying matrix operations by diagonalization. The characteristic equation. The characteristic equation is a polynomial equation that is fundamental in finding eigenvalues of a matrix. Given a square matrix A, its characteristic equation is dA minus lambda I equals 0, where lambda represents an eigenvalue. I is the identity matrix of the same size as A, and it denotes the determinant. The code defines a 2x2 matrix A and calculates its characteristic equation's determinant as a function of lambda value. It first constructs the matrix A, then computes logLn I with np.identity, and finally uses np.linealg.dedet to find the determinant of A, logLn I. While the code doesn't explicitly solve for eigenvalues, in practice one could use root-finding methods like the Newton-Raphson method to find the roots of the function characteristic equation logLn, which correspond to the eigenvalues of A. Diagonalization. Diagonalization is the process of converting a matrix into a diagonal matrix using its eigenvalues and eigenvectors. This is possible if the matrix has enough linearly independent eigenvectors to form a basis for its space. In the provided code, we define a function diagonalize that takes a matrix, calculates its eigenvalues and eigenvectors using np.lineal.ig, and forms the diagonal matrix D with eigenvalues. The matrix P consists of eigenvectors, and P_inv is its inverse. We reconstruct the original matrix, A' as PD P_inv to verify the diagonalization. In the example, we use a 2x2 matrix C, and the function returns its diagonal form along with the matrices used for the transformation. Eigenbasis and eigenspaces. An eigenbasis for a square matrix is a set of linearly independent eigenvectors that span the vector space. If a matrix has a full set of unique eigenvectors, it can be diagonalized using this basis. Diagonalization transforms the matrix to a diagonal form that displays the eigenvalues on the diagonal. The associated eigenvectors form the columns of the matrix that diagonalizes the original matrix. In the code, we define a matrix A and use NumPy's np.lineal.doc function to obtain its eigenvalues and eigenvectors. Next, we arrange the eigenvectors as columns in a matrix P and place the eigenvalues on the diagonal of a matrix D. We then reconstruct the original matrix A by computing PDP-1 to illustrate the principle behind the eigenbasis and diagonalization. The @ symbol represents matrix multiplication in Python. Spectral decomposition. Spectral decomposition is a matrix theory concept that allows us to express a square matrix as a combination of its eigenvectors and eigenvalues. A matrix A can be decomposed into a diagonal matrix L of its eigenvalues and a matrix V whose columns are the corresponding eigenvectors, such that A equals VAV manasuns. In Python, we can use NumPy to perform this decomposition. The code imports the NumPy library, defines a square matrix A, and then uses NumPy's lineal.eig function to compute the eigenvalues, evals, and eigenvectors, evx, of that matrix. After obtaining the eigenvalues and eigenvectors, we use them to reconstruct the original matrix A by computing the product V ed memasors, where V is the matrix of eigenvectors, L is the diagonal matrix of eigenvalues, and V nemasmor is the inverse of V. Finally, it prints the reconstructed matrix, which should be equal to the original matrix A if the decomposition and subsequent reconstruction were performed correctly. Applications to differential equations. Linear algebra, specifically eigenvalues and eigenvectors, plays a crucial role in solving systems of linear differential equations. Let's consider a system of differential equations written in matrix form. dx dt equals ax, where A is a square matrix. If we can diagonalize A, i.e. write A equals PDP1, where D is a diagonal matrix of eigenvalues and P is a matrix of corresponding eigenvectors, then we can solve the system more easily by dealing with independent equations for each eigenvalue. In the given code, we first import necessary libraries, NumPy for matrix operations, and scipy.lineal.xpm for computing the matrix exponential, which is crucial in solving the system of differential equations. The define matrix lambda function allows us to define the matrix A once and use it multiple times if needed. We set t as our time of interest for which we want to evaluate the solution. We call expm AET to calculate the matrix exponential of our matrix A times t, which gives us the state of the system at time t. This approach simplifies the process of solving the differential equations, especially when the matrix A can be diagonalized using its eigenvalues and eigenvectors. Orthogonal vectors and subspaces. In linear algebra, two vectors are orthogonal if their dot product is 0. Here's how to check if two given vectors are orthogonal using Python. The code defines two vectors v1 and vc2 using NumPy arrays. It checks for orthogonality by calculating the dot product using np.dot and compares it to 0. If the result is true, the vectors are orthogonal, otherwise they are not. Orthogonal complements. In linear algebra, the orthogonal complement of a subspace V in a vector space W with an inner product is the set of all vectors in W that are orthogonal to every vector in V. The provided code snippet defines a function is orthogonal to subspace that checks if a given vector is orthogonal to all vectors in a subspace. It then finds the orthogonal complement of the space spanned by vectors v1 and v2 within R3. The orthogonal complement is comprised of vectors in the standard basis identity matrix W that are orthogonal to both v1 and v2. Note that in this case, the orthogonal complement is the span of the third standard basis vector 001. Gram-Schmidt process. The Gram-Schmidt process is a method for orthogonalizing a set of vectors in an inner product space, most commonly the Euclidean space R3. This algorithm takes a linearly independent set of vectors and generates an orthogonal set of vectors that spans the same subspace. In the code, we define a function Gram-Schmidt that takes a matrix A whose columns are the vectors to be orthogonalized. We initialize a matrix Q of the same shape as A to store the orthogonal vectors. The function iterates over each vector projecting it onto the space orthogonal to the already processed vectors, and then normalizes the result. The projection is subtracted from the current vector q, and finally normalized to have unit length before being assigned to q. After all vectors are processed, q will contain an orthogonal basis for the span of the original vectors. Orthogonal projections. In linear algebra, the orthogonal projection is an operation that projects a vector onto a subspace. The orthogonal projection of vector y onto a vector v, when v is non-zero, is represented by the formula proja vy equal waf v do v. This formula comes from the dot product's properties and is used because the projected vector will be in the direction of v, but with a scaled magnitude. The result is the closest point on the line spanned by v, or plane depending on the dimensions involved, to the original vector y. The code calculates the orthogonal projection of a vector y onto a vector v using NumPy for array manipulation and dot product calculations. The dot product of y and v is computed and then divided by the dot product of v with itself to find the scalar projection. Then we multiply by v to get the vector projection. The result is the orthogonal projection of y onto the line spanned by v, which is printed as the output. The least squares problem. The least squares problem deals with finding the best approximation to a set of equations that may not have an exact solution. Usually, this occurs when we have more equations than unknowns, an overdetermined system. In linear algebra, we often represent this as finding the vector x that minimizes the norm ax minus b, where a is the matrix of coefficients, x is the vector of unknowns, and b is the result vector. The solution is given by the equation x equals a square plus b, where a square plus is the pseudo-inverse of matrix A. In this code, we use NumPy to work with matrices and vectors. We define a matrix A and a vector B. Because there are more equations than unknowns, we cannot find an exact solution. We calculate the pseudo-inverse of A using np.lineal.pinv, which gives us the ability to find the least squares solution by multiplying the pseudo-inverse of A by B. The result, vector x, is the optimal approximate solution to the equation ax equals b in the least squares sense, meaning it minimizes the sum of the squares of the residuals, differences between the observed and computed values of b. Orthogonal diagonalization. Orthogonal diagonalization is a process where we diagonalize a matrix using an orthogonal matrix of eigenvectors. This process is only applicable to symmetric matrices A equals AT in the real number space. The diagonalized form is very convenient for computations like raising a matrix to a power, as diagonal matrices are easy to work with. The code demonstrates how to perform orthogonal diagonalization using NumPy. 1. Define a symmetric matrix A. 2. Calculate the eigenvalues and eigenvectors of A using np.linear.a, which is suitable for Hermitian or real symmetric matrices. 3. Create a diagonal matrix D from the eigenvalues, for the matrix of eigenvectors Q is orthogonal for symmetric A. And 5. Confirm that Qt AQ equals D. The np.allClose function checks if the diagonalization is numerically accurate. Symmetric matrices. A symmetric matrix is a square matrix that is equal to its transpose. In other words, the matrix A is symmetric if A equals A squared T, where AT denotes the transpose of A. The elements along the main diagonal can be any value, but the off-diagonal elements must be such that the element in the ith row and jth column is equal to the element in the jth row and ith column for all I and j. In the code, we create a 3x3 NumPy array A, which represents our matrix. We then calculate its transpose A transpose using the NumPy attribute.t. We check whether A is symmetric by comparing the original matrix A with its transpose using NumPy's np.arrayEqual function. The output will be a Boolean indicating if A is symmetric. In this case, since A is equal to AT, the output will be true, confirming that the matrix is symmetric. Skew-symmetric matrices. A skew-symmetric or antisymmetric matrix is a square matrix A such that its transpose equals the negative of itself, i.e. AT equals minus A. The main diagonal of a skew-symmetric matrix must always consist of zeros. The code defines a function is skew-symmetric that takes a matrix as input and checks whether the matrix is skew-symmetric by verifying the condition A to T equal minus A using NumPy's allClose function for numerical stability. It tests the function with an example skew-symmetric matrix A and prints the result. Orthogonal matrices. In linear algebra, an orthogonal matrix is a square matrix whose columns and rows are orthogonal unit vectors, orthonormal vectors. One of the key properties of orthogonal matrices is that the inverse of an orthogonal matrix is its transpose. This means that if Q is an orthogonal matrix, then QT, Q transpose, is also its inverse, which is denoted as Q squared minus 1. Thus, QT2QQQT equals I, where I is the identity matrix. Orthogonal matrices preserve the Euclidean norm of vectors and are thus used extensively in numerical methods, particularly in transformations involving rotations and reflections. The given code sample demonstrates the verification of an orthogonal matrix using NumPy, a powerful library for numerical computations in Python. We define a matrix Q and calculate its transpose using Qt. Then, we verify its orthogonality by multiplying the transpose with the original matrix Q using np ... and show that the result is the identity matrix, which confirms the orthogonality of Q. The matrix chosen here is a simple 2x2 matrix that reflects across the y-axis, a common example of an orthogonal matrix. Trace and trace properties. The trace of a square matrix is the sum of elements on the main diagonal from the top left to the bottom right. This concept is used in various areas of linear algebra and has several important properties. In the provided code, we're using the NumPy library to work with matrices in Python. We define a square matrix A and then calculate its trace using np.traceA. This function automatically sums up the elements on the main diagonal of the matrix A, so trace A will be equal to 1 plus 5 plus 9, which is 15. Hermitian and skew Hermitian matrices. In the context of complex matrices, a Hermitian or self-adjoint matrix is one that is equal to its own conjugate transpose. A skew Hermitian or anti-Hermitian matrix is equal to the negation of its complex conjugate transpose. Mathematically, for any matrix A is Hermitian if A equals A, and skew Hermitian if A equals minus A, where A2 denotes the conjugate transpose of A. The code imports the NumPy library, defines a 2x2 Hermitian matrix H and a 2x2 skew Hermitian matrix S. To validate that H is Hermitian and S is skew Hermitian, it uses NumPy's all-close function to compare each matrix with its conjugate transpose, .conj, T for H and minus S conj, T for S. The np.allClose function checks element-wise equality within a tolerance and returns true if the matrices are approximately equal. Positive definite matrices. In linear algebra, a positive definite matrix is a Hermitian matrix all of whose eigenvalues are positive. For real matrices, this means the matrix is symmetric, equal to its transpose, and all eigenvalues are positive. A matrix A is positive definite if for any non-zero column vector x, the product xax, where x is the transpose of x, is positive. The provided code defines a function isPositiveDefinite that checks whether a given matrix is positive definite by computing its eigenvalues using numpy.linealg-eigvals. It then returns true if all eigenvalues are greater than 0, indicating the matrix is positive definite. The matrix A is used as a sample input to this function. Tensor product. In linear algebra, the tensor product of two vector spaces V and W over the same field F is a way to construct a new vector space, typically denoted VW, which relates to the original spaces in a bilinear manner. This operation extends to vectors and linear maps, and it is fundamental in many areas including quantum mechanics, representation theory, and differential geometry. The code demonstrates the tensor product of two finite-dimensional vectors using the NumPy library. We define the vectors u and v using NumPy arrays, where u is in R2 and v is in R3. The np.tensor function is then used with axes equals 0 to indicate that we want the tensor product, no sum over axes. The function returns a matrix where each element, ij, is the product of ui and vj, hence obtaining a matrix in R2x3, which represents the tensor product space R2, R3 in this discretized example. Normed vector spaces and inner product spaces. In linear algebra, a normed vector space is a vector space paired with a function called a norm. This norm satisfies certain conditions that allow it to measure the size of vectors within the space. The most common norms are the p-norms, of which the Euclidean norm, also known as the 2 norm, is a special case. Here's an example of computing the Euclidean norm of a vector in Python using the NumPy library. The provided code imports the NumPy library, creates a 2-dimensional vector, and then calculates its Euclidean norm using the np.linealg.norm function. This norm gives us the length of the vector from the origin to the point described by the vector in Euclidean space. Singular value decomposition. Singular value decomposition, SVD, is a factorization method applicable to any m by n matrix A. It expresses A as the product of three matrices, A equals USVV, where U and V are orthogonal matrices, and SE is a diagonal matrix with non-negative real numbers on the diagonal. These numbers are the singular values of A, and the columns of U and V are the left and right singular vectors of A, respectively. The code imports NumPy, which is a Python library for numerical computations. It then defines a matrix A to which we want to apply the SVD. The line USVT equals end linealgebra.svd A, full matrices equals false, computes the SVD of A, where U is the matrix with left singular vectors as columns, S is the vector of singular values, and VT is the transpose of the matrix with right singular vectors as columns. SIS is constructed by creating a diagonal matrix from the singular values vector S. The output U and VT are the matrices from the singular value decomposition of A. This technique is used for dimensionality reduction, noise reduction, and solving linear systems that are not necessarily square or well-conditioned. Jordan canonical form. Jordan canonical form, also known as Jordan normal form, is a particular kind of block diagonal matrix that is used to simplify linear transformations. It's only applicable over an algebraically closed field, such as the complex numbers. Every square matrix over an algebraically closed field can be represented in Jordan canonical form, which makes it a valuable tool for understanding the structure of linear transformations. The code provided uses the scipy.linealg.jordanform function to calculate the Jordan canonical form of a given matrix A. The function returns two arrays, J and P. J is the Jordan canonical form of the matrix A, where the eigenvalues of A are on the diagonal, and the superdiagonal may have ones if the eigenvalue has multiplicity greater than 1. P is the matrix of generalized eigenvectors that, when inverted and multiplied by A and then by P, will give the Jordan canonical form matrix J. This provides insight into the geometrical and algebraic multiplicity of the eigenvalues and the block structure associated with each eigenvalue. Quadratic forms and Rayleigh quotient. Quadratic forms can be considered as functions which map a vector x to a scalar, based on the expression x squared TAX, where A is a symmetric matrix. We can understand the nature of the quadratic form, definite, semi-definite, or indefinite, by looking at the eigenvalues of A. The code defines a function is positive definite, which uses NumPy to find the eigenvalues of a matrix and determines if all of them are positive. If so, the matrix is positive definite. A sampled 2x2 symmetric matrix A is used, and then it checks whether A is positive definite or not. Perron-Frobenius theory. The Perron-Frobenius theory concerns positive matrices whose entries are all positive and their leading eigenvalues and eigenvectors. The theory guarantees the existence of a unique largest real eigenvalue, the Perron-Frobenius eigenvalue, and that the corresponding eigenvector can be chosen to have strictly positive components. This theory has important applications in probability theory, matrix theory, and dynamical systems. In this code snippet, we are examining a simple 2x2 matrix to find the leading eigenvalues and eigenvectors in accordance with the Perron-Frobenius theory. We define a positive matrix A, then use the np.linealg.ee function to compute all the eigenvalues and corresponding eigenvectors of A. We identify the Perron-Frobenius eigenvalue as the largest eigenvalue and its associated eigenvector, which NumPy identifies as the corresponding column in the array of eigenvectors. This demonstrates the basic application of Perron-Frobenius theory using Python's NumPy library.